Hello, everyone. We have three guests today. We have Keith, which I will introduce in a moment. Three people on the stream: myself, Keith, and Saffron in English, my cat. Say hi to Saffron and say hi to everyone already in the chat. There's quite a few of you already joining and that we're waiting backstage. So one thing that I really like to do when we kick off those streams is to get a chance to have everyone saying hi in the chat from wherever they are joining us from. I am Benjamin and I'm your host for today. I'm joining from France, and let's see who we have in the chat. Let us know. Today the topic, and I think this is the last stream, the last Zephyr Tech Talk of the year of 2023. We will be back in January, but the topic for today is going to be Picolibc and all things C and all things C and small implementations of the C standard library in Zephyr. How can you make your code smaller, faster using a really cool open source library called Picolibc, which is something that Keith, our guest for today, Keith, hello Keith, is basically the creator of. So welcome on the show, Keith. How about you tell us a bit about who you are before we dive into the meat and
Absolutely. So my name's Keith Packard. I live in Portland, Oregon. I've been doing free and open source software for a while. My first GPL licensed project was started in 1984. So that's next year. I'll be celebrating my 40th year of GPL projects. Obviously, some of the projects that I had started before that year are still around, and that they predate the GNU public license, and so they don't use that license. I worked at MIT in the late 80s, early 90s on the X Window system, which is what I'm reasonably well known for, having worked on that for a long time. And I've been doing Linux, Unix, and graphics stuff the whole time since then. About 10 or 12 years ago, a partner and I started a business building embedded hardware for hobby rocketry and satellites, a system called Altus Metrum. And for that, we needed to have a C library for our embedded systems. And I looked around for embedded C libraries that ran on ARM systems, and I didn't find anything that I liked. I used a BSD licensed small C library for a long time, but that one really was designed for a small code size and not small executable size. I had looked at newlib for quite a long time, but newlib required a memory allocator for many of its functions. And in embedded systems, especially safety critical systems, having failure points like an allocator just really didn't satisfy us. And so I forked newlib and replaced the standard IO library with a different standard IO library and rebranded that as Picolibc. And it's really kind of taken on a life of its own. I didn't expect that the C library I was using in little embedded rocketry stuff would become something that other people would want to use. But I've spent the last 3 or 4 years kind of helping various RTOS environments transition from newlib or from their own internal C library to Picolibc. So Picolibc obviously runs on Zephyr, which has a fabulous community that we're chatting with today. It runs in FreeRTOS. It runs in Riot. It runs in a lot of other little RTOSes that I'm unaware of at this point. But the goal for Picolibc is to be a C library for smaller systems. And that means systems that aren't really designed to run a Linux operating system or other kind of real big multitasking memory managed operating system. And so I really wanted a system that that focused on memories and code size, but was still completely conformant with the relevant standards. One of the things that's really easy to do is to take shortcuts in the standards and provide an implementation that surprises the user or does things that the code doesn't expect. And so we have a standard for the C library. The C language includes the C library as part of its standard. There are obviously extensions to that standard. POSIX is a very popular one. And so where relevant, Picolibc uses those standards and conforms to them as closely as possible. So I've been working on this for the last probably 5 or 6 years, off and on. It's really is associated with my fairly small rocket and satellite software and hardware business. And it's not associated with my day job very much, although I have gotten it running with FreeRTOS. And I believe Amazon is starting to ship a couple of projects with Picolibc embedded in it. But this really is an evening time, weekend time project for me, not really associated with my Amazon work. I guess I should say that I'm a senior principal engineer at Amazon in the Device OS organization.
Yeah, let me put your slides on the screen, and you can go through them as you wish. So yeah, interesting, the rocketry stuff. I guess for you, the C standard library is more than just like string manipulations and like printf, etc. It's also all the math, right? Like
Yep.
and how far can you go with Picolibc when it comes to all the geometry stuff, etc., that you might need for your rocketry computations? Like, are there other libraries that you use on top of Picolibc for fast, complex maths?
Not at this point. We are not doing rocketry guidance. We're just doing rocketry tracking.
Telemetry
and so our the telemetry and we have an IMU measuring the state of the rocket, and actually tracking the orientation, position, and velocity of the rocket. But we aren't currently controlling it, although we're planning on doing that in the future. It actually turns out to be the tracking and maintaining the state of the rocket turns out to be pretty complicated. And so I am using quaternion based math to track the gyroscopes and magnetometers, and integrating those together to track the state of the rocket. And so there's quite a bit of math there. Most of that has been handwritten because quaternions, there isn't really a great library for supporting quaternions yet. But of course, it does use trigonometry to take the gyro data and convert that into the quaternion state vectors. So I use quite a bit of the math libraries, obviously using a lot of the string manipulation stuff. And for kind of the core of the core of the interest for Picolibc was the fact that during debugging, you really want to be able to have printf integrated into the system, just to make it easier to print out values. The fact that I'm doing a lot of math with a lot of floating point stuff means that I really need to have competent floating point printf for debugging of the system. I don't like to use two different firmware loads for debugging and deployment. And so I really do have printf in space at this point in both rockets and satellites. So that was turns out the printf is kind of the hardest part, well, one of the harder parts of a C library.
Interesting. Okay, so yeah, a reminder to our audience that, well, if you feel like introducing yourself and saying hi in the chat, please do so. But maybe more importantly, any questions you have for Keith, just drop them in the chat and we will probably take them as they come.
Yep.
So yeah, like I think we were briefly discussing offline before starting the stream. I think it'd be great today, especially since our audience is probably mostly Zephyr folks, to get, I mean, just a general update of where things are at with Picolibc, maybe chat a bit about the integration with Zephyr and what's happened recently, and talking about the future as well. So, I mean, in no particular order, feel free to.
I've got a couple of slides here to talk about that. Until we start getting some questions, I can just start giving information about the library. Of course, my robot vacuum is attacking me right now.
I was wondering what that was.
I'll try to send it out of the room. It's found an HDMI cable. Let me actually get it out of my office.
And hello, Roman from Switzerland. Hello, Buddy from Vienna, Austria. We have Italy, we have South Africa, Denmark. Hey, lots of European folks. I see Paul from the US. But yeah, let us know in the chat. And yeah, robot situation handled, hopefully.
Yeah, the robots we live with. I wish that was running Zephyr, but I don't believe it is. As I said, Picolibc is a C library targeted for embedded systems. Um, Benedict Schmidt asks a question that newlib has already been used in Zephyr, and Picolibc is basically a fork. What's the main advantage of using Picolibc? It is code size and standards conformance. So Picolibc replaces kind of the most expensive parts of newlib, the standard IO library, with a standard IO library that's targeting embedded systems. So it does not use malloc for printf. It only uses malloc when you actually allocate objects in the standard IO library, like a file object. That's the only place where malloc occurs. And that means that there's no possibility of failure in the middle of the library while operating things. One of the key technologies in Picolibc is the replacement of the floating point decimal to binary conversion algorithm. Kind of the C standard requires that the binary to decimal conversion be round trippable, which is to say when you print a value and read it back in, you're supposed to be able to print and then scan and get exactly the same bits as a result. And if you starting in that standard was updated, I think, for C99. And at that time, everybody was using arbitrary precision arithmetic to do that. And arbitrary precision arithmetic, it's right there in the word, it says arbitrary, and that means there's a malloc inside your printf code. It turns out that about 5 years ago, an engineer wrote a new floating point algorithm called the Ryu floating point printf algorithm. And that does not use malloc. It uses a fixed amount of memory to do the decimal to binary conversion, and it's exact, which is to say round trippable. But it has compromises in exactly how it represents the binary number in the output. So when you add more and more and more digits, it's not gonna keep adding decimal digits. It just pads it out with 0. It finds a representation that it can convert back to the internal binary representation and prints that, and then stops doing the conversion. So it has fixed limited number of digits output. But those will exactly represent the binary number when scanned back in. The other thing that Picolibc focuses on is testing on embedded systems. So Picolibc has an integrated test suite, and that test suite tests as much of the library as I can, and I keep adding more tests. I just added more tests this week. And that runs actually using QEMU or other emulation technologies on the target system. So I actually run, at this point, from a Zephyr perspective, I'm running, I think, every single one of the Zephyr targets that Picolibc supports under emulation using running the test suite for every commit. So that means that Picolibc is validated on the targets that we use in embedded systems for every commit.
Nice. Before we take Alexei's question, maybe obviously that wouldn't be the case for Zephyr, but how about 8-bit MCUs? Like, is this something that's still somehow on the radar, or like it's a thing of the past and you don't plan on maintaining that?
So it is interesting that I mentioned 1632 and 64-bit processors. There's a really super popular processor called from Atmel called the AVR, like Atmega 328.
I was thinking about this one. Yes,
exactly. Those are notionally 8-bit in that the registers are only 8 bits, but when you compile C on them, they actually pretend that they're 16-bit processors. So Atmel is actually one of the targets that Picolibc builds for. And I think some user was trying to get it to actually be able to build all of the tests and run them. I'm not sure what the status is at this point. But yeah, the Atmega is one of the targets. So Atmel actually is where the printf code for Picolibc started. The kind of the focus on tiny size of the printf implementation started with the Atmel implementation. That was free software under a BSD license, so that was integrated into Picolibc. It's been changed kind of dramatically since then to gain more standards conformance and to extend its functionality quite a bit. But that's kind of where it started. So I think the Atmel C library is still significantly smaller than Picolibc, especially the math functions. The atmel math functions are significantly less precise, but they are also significantly smaller. So if you're building atmel processors with the 32 kbytes of ROM on the really tiny ones, then you probably want to continue using the atmel C library. It is quite a bit smaller still.
Yeah, I've always wondered, like, since the first days of Arduino, like the fact that in those super tiny Arduino sketches, you could do printfs for floating numbers without having to think about it too much. That was almost
Yep.
scary, but yeah.
Yep.
Do you want to take
Well,
Alexei's question in the
absolutely.
chat? Let's put it on screen.
Yeah.
Speaking of conformance to standards, earlier you were talking about like the reciprocity of printfs, scanfs, and stuff. Yeah, which one of the C standards do you conform to, basically, and validate?
That's a good question. So I talk about focus on C and POSIX conformance. I actually validate against. I think I'm using C17 at this point as the validation target for Picolibc. And so the test suite, the integrated test suite inside of Picolibc targets the C17 standard. I haven't the C2X standard that's coming out soon adds a huge number of functions to the math library. And I haven't really started working on that yet. It would be awesome to get some help with that because it adds decimal functions and a huge number of other math library functions that are going to take a lot of time to implement. So it's C17. I build and test with GCC and Clang in C99, C11, and C17 mode to make sure that it works with those various versions of the language. But the standard conformance is all focused on C17.
Okay.
And then for areas where the C library doesn't cover functions like stir and compare and other functions that come out of POSIX, and I obviously look at the POSIX standard for conformance there. For some cases, the C standard is a little vague, and the POSIX standard has more specifics for some error value returns in a lot of functions in particular. And so those functions are going to be POSIX conformance because the C standard isn't as specific as POSIX.
Yep.
And look and see what else I have. Okay, let's talk about what's going on in the current version. The current version 1.8.5 was really released to support Zephyr. I released this back in September. I finally figured out what the basic problem was. There are 4 different printf configurations in Zephyr, and Picolibc supported 3 of the 4. Which wasn't helpful. And in fact, the default configuration where printf doesn't have floating point support, but does have support for all of the integer sizes, that was the configuration missing from Picolibc. So 1.8.5 finally adds that configuration. That's been integrated into Zephyr. I wrote these slides a week or 2 ago before Zephyr had actually updated to this particular version. And so this is all available in Zephyr today. That was really the reason for this particular release, was to get that final printf configuration available. And so now, the printf configurations are selected in a very strange way, and maybe we should fix that in Zephyr. You go in and select the CB printf requirements that you have, and those then end up driving the Picolibc configuration. You can then go in and increase the printf support, but the CB printf requirements are kind of a floor of the printf functionality. So it's maybe we should try to figure out how to clean that up. But the fact that Zephyr has an integrated non-standard API that uses printf semantics called CB printf means that the Picolibc has to support the Zephyr API. And so Picolibc has to have at least that level of support, which is why the CB printf specifications kind of control what Picolibc does. It's a little weird, and maybe we should probably document how this works so that people understand how to configure the library. This is actually supported in the SDK, so you can actually change the printf configuration and the amount of memory that printf uses at build time, and not actually have to build the whole library. So that's kind of a nice feature. So you get a a super customized library without actually having to build the library as part of your project.
Are there other options like that that can be used to configure without having to necessarily rebuild?
I don't think so.
Should there be?
Yeah, I think that's a really good question. So in the Debian version of Picolibc, I actually deliver two different builds of Picolibc. I deliver both the min size and the speed optimized version of Picolibc in Debian, and you can choose which of those two versions you use at build time. We should probably chat with the SDK maintainers in terms of whether that would be useful. The size optimized version of Picolibc uses the tiny version of all the string functions. And so they're not terribly fast, and there are actually some performance gaps there that might be interesting to close. One of the things that I did. So we all remembered the Drystone benchmark. The Drystone benchmark turns out to be a stir compare benchmark. I think that's the string function that it's basically benchmarking. And so because of that, in order to make several customers happy, even the size optimized version of Picolibc, by default, it uses the speed optimized version of the stir compare function so that the Drystone results aren't impacted by that. Kind of a kludge. But so Picolibc inherits all of the size and speed optimized assembly version of the string functions from newlib. And so we have a custom assembly for all of those functions for ARM in particular and for RISC-V. So kind of our two key Zephyr architectures have some really good functionality there, but only in the speed optimized version of Picolibc, which is not what we're building in the SDK now. So obviously, if you integrate, so Picolibc can either be built into your project as a module, or it can be pulled in from the SDK. If you build it as a module, you're going to add all 1,100 files of Picolibc, the Picolibc build to your project. So all of a sudden, the number of files you're compiling goes up by a lot. But that does let you get the speed optimized version of Picolibc and also make a lot of lower level fine grain configuration of Picolibc possible. Let's see. I'm going to talk about some of the recent work that I worked on in Picolibc. So one of the things that I worked on for 1.8.5 was shrinking the printf code even more. So one of the things that one of the changes in 1.8.5 was to support the printf of 64-bit integers on 32-bit targets. And the kind of the naive way of doing the 64-bit integer to decimal conversion is to use a division and a modulus operation. Well, for a host with only 32-bit ints, you have to fall back to the software int division code, which is huge. It's about 800 bytes. And so I actually went in and wrote a custom div and mod function for the the binary to decimal conversion that does some pretty fun math there. I've just got a patch queued now that actually comments how that works. So the printf code using 64-bit ints on a 32-bit target doesn't even use the soft integer division code. So you saved it 800 bytes. The replacement code's about 100 bytes long on Cortex M3. So you do save quite a bit of memory there. The other really key thing for Zephyr here is that I added a bunch more testing targets. So now Picolibc is being actually tested on all of these additional targets for 1.8.5. And you can see several of those are the NIOS2 and ARC targets in particular are part of kind of the core Zephyr infrastructure. The M68K target was a lot of fun to get working. And the MSP430 target was also interesting. The M68K has some very interesting floating point modes that nobody else uses. Which means that all the work that I did there is pretty much not useful for anybody who's not using M68K, which is essentially nobody. But it was really fun. The nice thing about a hobby project is you get to do things. That don't really affect a lot of users, just because they're technically challenging, and that was definitely that. The MSP430 was interesting because the compiler there actually has several different floating point modes in the compiler. You can either have 32-bit float, int, and float double and long double. You can have 32-bit float and double and 64-bit long double, or you can have 32-bit float and 64-bit double and 64-bit long double. And getting Picolibc to be able to compile to all these strange and anomalous floating point modes, that was quite challenging. But it means that the support for ARM's 64-bit double, 64-bit long double is a lot cleaner now. And it also means that if we do find another target that wants to use 32-bit doubles, that Picolibc is ready to go. And that's something that I haven't seen another C library try to tackle that in any sort of way. The other thing that I did to Picolibc was I actually added GCC's fanalyzer flag to the CI system. I have a friend who works in Linux security, Case Cook, and he kind of pokes me with occasional GCC or Clang debugging flags or validation flags, and this was the latest one that he sent at me. He has tried this on Linux once, and he got thousands and thousands and thousands of warnings. Most of them were too complicated to try to parse. But I said, I'm just going to go for it. So I turned it on and I fixed all of the warnings that it was emitting. And I think I found 3 or 4 real bugs here. So that was an enormous amount of work to get rid of the false positives, the warnings that it was popping up that weren't actually problems. But it's really useful to do as much validation with the compiler as you can. And the fanalyzer flag is an interesting value. If any of you have played with that, it's actually trying to do kind of abstract interpretation of your code to figure out where bugs might be. So it's looking for use after free problems. It's looking for memory leaks. It's looking for buffer overruns, doing static analysis of your code, and it does whole function analysis. I mean, whole file analysis. So it's able to find bugs that are cross-functional. And it's interesting to play with. It really has some interesting opinions about how C works. So that was a good thing to add.
Speaking of fixing bugs, Fabio is asking how often and how many compiler bugs have you bumped into while working with Picolibc?
So I have found bugs obviously in Picolibc. Most of the bugs are actually in the C library, which is good because that's code that I control. But I have found bugs in QEMU. I have found bugs in the M68K math library that GCC ships, and I have found a number of compiler bugs. Yeah, so doing CI like this and running CI across so many systems means you kind of close the loop, and you do find bugs in lots of places. So I feel like in the Debian work that I do, where I deliver the C library and the QEMU packages and actual applications, that by and the tool chain. So I ship the tool chain, the library, and the QEMU stuff in Debian, and so I'm able to kind of close the loop and build code that runs under emulation with a particular compiler, and kind of make sure that all 3 of those work together. And that feels like a really powerful way to make sure that the library, the compiler, and the emulator are all doing the right thing because they all agree. So yeah, I find bugs everywhere. The frustrating thing I have with GCC is that it's very difficult to get patches merged for embedded targets. Because the bulk of the GCC community work is obviously focused on kind of more important targets. And so getting, for instance, I've had Picolibc support for GCC queued for 2 years now, and I kind of poke at it eventually, but the GCC community doesn't seem excited about it. So that particular community is kind of the most challenging one I have to work with. The QEMU community is pretty easy to work with. I've got the RISC-V semi-hosting support integrated into QEMU. I've got the M68K math bugs in the emulation fixed, and I regularly post patches to that particular project.
Nice. And speaking of community, do you get a lot of community contribution to Picolibc, and or are there any areas where you are actually looking for help from the community?
Yeah, I do get. Yeah, I do get quite a few contributions from the community. I'm not a huge fan of proprietary software, but the community effect of having Picolibc available on GitHub has been really powerful. And I have to credit the fact that people can use that software, either GitHub or GitLab, and provide drive-by commits for things that they find in their particular targets. And so I'm super happy to take one-off patches into Picolibc from people that just found a problem in their particular project using Picolibc in a particular environment. And so I probably get 3 or 4 patches a month from people outside, using Picolibc in various places. There's a contributor from Google right now working on a bunch of Picolibc support for the Cherry operating system, which is kind of fun to watch. I had a bunch of support for the Super H architecture done externally. I've had some RISC-V support and patches by people working on RISC-V stuff. So it's kind of fun to see what people are using Picolibc for, and to get patches from people that have found ways to make it work better for them. That's a great thing to do. One of the areas that I'd really love to be able to do is to spend a bunch of time working on the math library for targets without FPUs. It turns out that it is pretty straightforward to write the math library in ways that use mostly integer operations. Most of the math library is just these polynomials evaluating, approximating functions for trigonometry or whatever. And it's fairly straightforward to do that in integer-only arithmetic instead of using floating point for all of that. And a conversion or a separate implementation of all the math functions that used integer-only operations would be dramatically smaller and a lot faster on targets without FPUs. So that's kind of an area I would love to see. I'd love to see some work done. If anybody is excited about integer-only targets, I would love to provide some pointers, and then work on getting that integrated into the library. Right now, all of the math code assumes that you have an FPU because it's all written in floating point. And if you don't have an FPU, then you're calling all the soft floating functions for every single operation, which is pretty redundant given that the magnitude of the values used there are all known. And could be encoded outside of the operation. So instead of encoding them in the floating point number, you just encode the exponents outside and do the math just using integer operations. So that would be super fun to see.
By the way, you mentioned briefly open source like GitHub, etc. What's the license of Picolibc, by the way? Because there's a history of probably
Yeah,
lots of GPL in
history
the
of
C
licenses.
world.
Yeah. So NewLib came out of some Cygwin work, some Cygnus work back in the 90s. And Cygnus was a company bought by Red Hat that did toolchain work. And so Cygnus needed a C library for non-Unix systems. And so they wrote NewLib, which was the new C library back in the 90s. And Cygnus was a heavily GPL company, but a lot of the NewLib code came from the BSD world. And so the bulk of the C library functions in NewLib were under the BSD license. The OS specific part written by Cygnus, almost all of that was GPL'd. And so the NewLib code is kind of this mishmash of the core library being all BSD licensed, and all of this OS infrastructure called libgloss is all GPL licensed. And so when I forked, when I pulled in the NewLib code, I only pulled in the library code, and all of that code is BSD licensed. And so all of the GPL code that was in libgloss and other parts of NewLib, none of that exists in the Picolibc repository. So Picolibc is purely BSD licensed. I went through. There's actually a file at the top of the Picolibc repository called I think it's called copying.picolibc, that actually enumerates every single file in the library and describes which license it uses. It uses the Debian copyright file format so that it's machine parsable. But it explicitly licenses every single file in the library. I couldn't find any way to do this in a way that was simpler. There's a script that I use to actually go through and read every single source file and try to figure out what license it's using. And then I validated every single one by hand to make sure that they are all licensed correctly. So the code that gets built into Picolibc and integrated into your application, all of that is purely BSD licensed and clearly free software and clearly redistributable. There are there's a script that helps you build a Meson configuration for Picolibc that is AGPL licensed in the repository. And there's one test case for the printf code that is GPL licensed. Those are not actually built into the library. And so those don't impact the license of the application that uses Picolibc at all. I could delete the script pretty easily, but it is convenient for people using Meson. And I actually know the author of that particular printf test suite. And so if I actually had a legal opinion that told me that I needed to fix the licensing so that there wasn't any GPL code in the repository, that would be possible as well. But I haven't needed to so far. Zephyr in particular is pretty careful with licensing, and the Zephyr community went through the Picolibc licensing pretty carefully before accepting it as a module, and now as a deeper core dependency in the system.
Cool. Quick question from Sandra, going back to the floating point topic. I don't know if you've run Picolibc on old Intel Pentium, for example, but have you run into bugs in any SoCs around floating point hardware? And if yes, needs for working around those bugs?
That's an interesting question. I don't think so. One of the nice things about the IEEE floating point standard is that it's pretty rigorous, and it's very detailed in exactly which bit representations are going to come in and out of the hardware. So if those of us old enough to remember the Pentium FOOF bug will remember that some hardware implementations of the floating point standard did have bugs, but I haven't found any in my work. The only place I found floating point bugs is in the M68K software float emulation that's provided in QEMU. And in the M68K math libraries that are provided with GCC. So I found some emulator bugs in floating point for non-standard floating point that comes in the M68K. But all of the IEEE floating point hardware and software that I've used has been pretty darn standards conformant. Picolibc tests a lot of the floating point bits. In particular, one of the things I spent a bunch of time working on was the exception support in Picolibc. And exception stuff in the IEEE standard is a little wonky. And so the one place where Picolibc has this, I don't know if it's I don't think I could consider it a bug because it is nominally IEEE conformant, is on the older x86 where they did all the floating point operations in 80 bits and then converted them back from 80 bits to 64 or 32 bits when you stored them. And on that particular target, the handling of quiet and signaling NANDs is a little wonky. And so Picolibc has some tests that it actually skips on that particular target because it does things a little strangely. In particular, when you just load a signaling NAND into the hardware and store it back into memory, because it goes through this type conversion from 32 to 80 back to 32 or 64 bits. That type conversion raises an exception and converts the signaling NAND to a quiet NAND, and there's nothing I can do about it. And so Picolibc actually has a couple of tests that it skips because of that oddity. It is nominally conformant with the spec, but it's definitely unexpected. It's like I'm just literally loading a value into a register and saving it back out again. Why is it changing the representation of the data? But it is notionally conformant. Oh well. So I think actually this has now been released. I think all of this has been released now. There is as I said, the MSP 430 had this weird floating point configurations that stuff got extended, and then there's some Super H and Spark testing. Picolibc CI is run on 32-bit Spark, but it's not Spark 8, but it's not yet run on Spark 9. I don't have the Spark 9 infrastructure running yet. I'm sure there's a huge number of people interested in embedded systems with Spark 9 processors, and I'm sorry that it's not ready yet. The other thing is that I finally added long double decimal output to the floating point printf stuff. This is not standards conformant. It kind of exists to make sure that there's not a gap in the support in the library. So eventually I may spend the time to go in and make that precise. I know how to. It's just a bunch of niggly work in the exact implementation of the RIU algorithm, which is very sensitive to the size of the data. Zephyr stuff. I think this is probably an area of a lot of interest here, oddly. So the Picolibc is now the default C library. So if you just take a Zephyr project and don't configure which C library to use, now you get Picolibc instead of what you used to get. You used to get kind of an internal, not quite standards conformant C library called the minimal C library, and now you get an actual standard library that does everything that a C library should do, and it's enabled by default. Malloc in Picolibc works by default. So if you don't with the minimal C library, if you compiled your application with the default configuration, Malloc would exist, but it would always return failure. And when you build with Picolibc now, Malloc gives you a little heap so that at least you can do some small allocations. That means that when you're transitioning a project from kind of the old world into the new world, if you are calling Malloc, you're now going to get a real functioning Malloc, which means your programs can use a bunch more text space. Not only that, because of the way Zephyr links Malloc, I have a patch for this. I'm hoping to get it reviewed. But because of the way that Zephyr links this stuff, even if you don't call Malloc, the Malloc heap gets initialized by default. And so there's a bit of code run at startup time to set up Malloc in case you do call it. And that always gets linked into your application unless you disable it. So I had two different patch series posted to Zephyr. One of them was to change every single test that didn't use Malloc to disable Malloc. And that seemed like a pretty invasive change. And the later patch series that I've done is to fix it so that if you don't call Malloc, then the Malloc heap doesn't get initialized. And I'm hoping that series is going to get reviewed and merged pretty soon. That means that you wouldn't have to worry about whether your application called Malloc. If it called Malloc, Malloc would work. If it didn't call Malloc, there'd be zero overhead. The other thing that's important about Zephyr, the Zephyr integration, is that the thread local storage. This isn't the security library. This is thread local storage. There has been a PR merged recently that allows thread local storage to be disabled, but by default it is enabled. And that actually changes Zephyr in some pretty low-level ways. Zephyr actually uses thread local storage when it's available for a bunch of its internal OS operations. And so when you enable thread local storage, then a whole bunch of the internals of Zephyr change. And so if the issue here is that in the transition to using Picolibc by default, now you also get thread local storage by default. And that may actually have an impact, especially on architectures that aren't as heavily tested for their thread local storage support. So we have found bugs in the ARC thread local storage code recently that were uncovered by this. So that's something to be kind of aware of as we make this transition. Okay, so this is the other one, right? So some pending Zephyr work. I want to leave Malloc enabled by default. I should have fixed this up yesterday because I just changed this. I want to leave Malloc enabled by default, but to make it not cost anything. So I have another PR posted, and I can go figure out which one that is. That one needs some review by by somebody competent with CMake to make sure I'm not doing anything that won't work in general. But I want to make it so that Malloc can be enabled by default, but not cost anything if you weren't using it. That one needs some review by people who understand CMake, so I could really use help with that one. Picolibc, the 1.8.5 62.882 has been merged. That was merged a couple weeks ago. There's also another patch for some code checker fixes. Picolibc, the code checker is this static analysis tool, and and it uses sparse, I think, as one of its steps. And that analysis is breaking on Windows when using Picolibc. I can't figure that out because I don't have any Windows environment that I can build Zephyr in. So if people want to go poke at 62.318, that would really be helpful. I should go find the Picolibc patch that I am hoping to get into Zephyr. That's a pretty, oddly, I had this search. Yeah, it's 65.434. Don't use whole archive for libc comment and libpicoc files. When Zephyr links stuff right now, basically the entire operating system is linked with this whole archive flag, which pulls in all of the code for every single piece of the system. And then we use this garbage collection, the library garbage collection thing, where you basically take all of the roots, all of the global symbols that are actually being used, and kind of shake the tree, and so that symbols that aren't being referenced get dropped on the floor and deleted by the linker. That works great. It's a really easy way to link stuff. It means that all your circular references between files aren't a problem, and it resolves all of those. The problem is that any of the code that is marked keep by the linker, which is to say anything that any of the static, any of the uh, uh, constructors or destructors that are in the application, every single one of those in any of these libraries gets included in the result. So even if you don't use the functions that require that functionality, like malloc, all of those constructors get included in the linker. And so that's why the malloc stuff gets included in your application when you build with Picolibc enabled. And so by taking those little bits of code and moving them out from the whole archive list, that means that the keep blocks in those all of the constructors, they only get linked in if some other symbol from that same file is referenced. And so the malloc code has the constructor in the malloc code. So if you don't ever call malloc or free, then that file doesn't get linked into your application. And so the constructors don't end up being visible to the linker and getting stuck into the result. So it's a pretty simple change. And I would love to get somebody with some CMake expertise to take a look at that and help get integrated. Other than that, my list of stuff to get integrated into Picolibs, into Zephyr is pretty short today. I've really been happy with working with the Zephyr community and the liveliness of the community and the fact that there's a functioning group of people who can review even deep changes to the operating system. The thread local storage stuff was really fun to watch get integrated. I posted this patch that just used the Picolibc internal thread local storage stuff just for Picolibc. And the Zephyr community took it and ran and embraced the thread local storage stuff and integrated into the operating system in a really fundamental way, which was really fun to watch. Let's see. Okay, so future plans. As I was talking about, I would love to have the math library. Right now, there's some kind of corner cases in the math library that are really inaccurate. I'm sure everybody uses the gamma function on a regular basis in all of their embedded code, but that particular function has some really big error bars on it right now. I think it's the 64-bit version is probably good for 30 or 40 bits maybe. So it's got some pretty bad error bars on it. So I would love to kind of have a scalable precision and accuracy in the math intrinsic somehow, so that we could choose between speed and accuracy. There's a project out of CERN, I think, that tracks accuracy in floating point math libraries across a bunch of different libraries. And you can see that the Picolibc and newlib error bars are much wider than glibc and some other C libraries, muscle and things like that. It's obviously a compromise between accuracy and performance. The glibc polynomials are quite a bit longer than the newlib polynomials. As I talked about, Picolibc has long double printf and scanf support, but it's not round trippable. It's not the same as the 32 and 64-bit stuff. So I would love to spend some time adapting this Ryu algorithm to 80 and 128-bit floats. That's a bunch of work. It's actually not. It's a bunch of reading code and understanding constants and figuring out how to adjust the code to use bigger numbers. And there are some, as I said, there's a couple of Zephyr issues. The integration of Picolibc into Zephyr has uncovered kind of a number of bugs that people are finding, and we're trying to fix those as quickly as possible. And I think we're on keeping track of those pretty well. But going forward, we just need to make sure that we track bugs that are in bugs that are occurring because people are starting to use Picolibc more. So it's going to be fun to see what people come across going down the road as it gets used more and more in Zephyr.
There's a question from Georgia relating to floating point math. Picolibc has switched away from explicit and implicit double casts that existed in ULib. Has there been any testing on the loss of accuracy due to those changes?
That's a really good question. So I don't know if Georgie is thinking about the same part of the code that I'm thinking about, but about 5 years ago or so, ARM submitted some patches to NewLib to change how some of the intrinsics were computed. So the ARM code uses 64-bit doubles to do some of the 32-bit intrinsics in the math library. So things like the exponent function and I think the sine and cosine functions. They re-implemented them using 64-bit math instead of 32-bit math. I have no idea why they did this. I mean, the ARM M4 processor in particular, one that I use a lot, only has a 32-bit FPU. Why would they submit code that required a 64-bit FPU when you're using 32-bit values? It was a mystery to me. I would love for somebody to explain why they did that. So that code, on a system with a FPU that was kind of optimized for 64-bit operations, that code, the polynomials can be smaller because each polynomial, you don't lose as many bits in each computation because you have a lot more precision available. I did some analysis of the precision of that code. It's actually less precise than the old 32-bit code. So the new math code provided by ARM, I assume it was for performance because it uses 64-bit values instead of 32-bit values, and it does fewer computations. But that code actually ends up being less precise than the old code that came from Sun from the 90s. And so that's disabled by default in Picolibc. It's still there. If you want to go experiment with it, if you have a target where 64-bit math is super awesome, and you don't need all of the precision that the existing code supplies, you can build that. I think it's probably available as an option when building Picolibc as a module. I'm not quite sure. So that's there, but it is actually less accurate. Let's see. And yeah, so as I said, I do test the accuracy of those. The math library tests actually have explicit error bars on every single test so that it makes sure that the values being computed are within the expected range. I validate those tests using glibc as kind of an oracle to see if I'm getting reasonable numbers. And so the CI actually runs all of the math library tests on NewLib on all of the platforms that NewLib runs on, and it also runs the math tests using glibc on the host platform. So I'm making sure that the tests are the same on glibc and Picolibc. So we get an additional validation there.
Great. Well, we are almost at the end of the hour. I'm pretty sure there are folks who have still some questions. I mean, there were some really, really good questions, so I would be shocked if there's not a couple more. But we can also start wrapping things up. I would like to remind everyone that I think this is the 7th or 8th episode, so there's lots that you can catch up on, especially with the holiday season that's coming. Lots of tech talks. We yeah, we've been doing those every other week, and in the new year, we'll try to make those weekly, hopefully. And this is also a call for everyone to participate if you want to submit, and if you have an idea of something that you would like to present. I'm putting the link right below. If you go to the zephyrproject.org/propose a tech talk, that's just fill in the form, share your ideas, and I will follow up with you. Subscribe to the YouTube channel. This is always appreciated, and it's also a really good way to be notified when we have upcoming content. You can put some likes as well. We always love to see those. I'm pretty confident that this session will have a long life and a long tail, because it was lots of really good information that Keith, you shared with us. Let's see in the chat. Yeah, George, thank you for the answer, and he adds that it might be interesting to test these with the variable size floating point library in the future, and that makes you laugh.
So a bunch of the numbers, a bunch of the validation for the long double math, I actually did the computations there using a language that I implemented called Nickel, which provides arbitrary precision floating point numbers. And so I do those computations in 512-bit arithmetic, 500 as a 512-bit float. So I have a lot of experience doing really big floats with that particular language.
Pretty cool. Okay, so I think this is it. By the way, our third guest or whatever participant is slightly waking up ish. If you're watching the recording, feel free to drop questions and comments in the chat, and we will make sure, especially if those are questions, we will make sure to send them Keith's way, so that you get an answer. And with that, Keith, it was a really good chat. We should do that again in the future when Picolibc 2.0 is out, maybe, and when you have super awesome. Yeah.
Thank you so much. This has been a lot of fun, and I appreciate all the really awesome questions. And I look
it was
forward
pretty awesome.
Yeah.
And this is the first time that we are wrapping it up on time with 3 minutes left. Thanks, everyone. And we will be back sometime, maybe not the first week, but the second week of January. Have a great holiday season if you are celebrating. Thanks, Keith. And thanks, everyone. Bye.
Thanks so much.